that will enable future missions to deploy radiation monitoring equipment much more broadly than has been done in the past. So the name was inspired by the radiation assessment detector that was carried on the Curiosity rover, which was used to survey the Martian radiation environment both once the rover got to the planet, but also to assess what the radiation dose would be on the journey to Mars. So sort of following on from that basic concept of being a very generic, broadly applicable radiation sensor that can tell you a lot about different types of particles and measure the energies of those particles, we decided to name our payload MicroRad, reflecting that it has, as much as possible, similar capabilities, but in a much smaller package.
What were the challenges of taking that standard radiation detector and sort of getting it down to that very wallet-esque size payload, which you accomplished?
So there were definitely a lot of challenges, both implementation difficulties. For example, the chip shortage really caused us a few issues, but also technically as far as getting the capabilities we wanted in such a small package. But thankfully, we were able to leverage some novel technologies that really only became available in the last couple of years to do that. So that was definitely a challenge. Basically, how many new technologies we were trying to leverage and cram into such a small payload and also do it with such a small team and on such a short schedule.
Christian, what are some of the broader uses for the technology you've developed for URAD?
So URAD is very unique as far as being very low cost and small size. And it's also not specifically focused to any one type of measurement. So it's very good at characterizing sort of a general radiation environment. And that sort of lends itself to a lot of other applications beyond the immediate needs of NASA or the immediate needs of the Artemis program. Potentially, I could see applications related to national security, for example, assessing whether someone's trying to smuggle radioactive material into a port, for example. But there's also other applications in space. For example, it's small and cheap enough that you could put one on a large number of spacecraft, and then that would give you spatial diversity as far as the radiation measurement, which could be useful for understanding the structure of CMEs, perhaps, or perhaps it could be used for being able to discriminate between hostile anti-satellite action versus natural effects as far as when radiation effects show up on a spacecraft, being able to tell, is someone pointing a particle accelerator up at the satellite, or is that the radiation that's just coming naturally from the sun, for example.
Christian, thanks so much for taking the time to explain URAD. Next, let's talk with Phil, who has SunSlicer. Phil, can you tell us about SunSlicer?
Hello, Blair. Yes, SunSlicer is a miniaturized X-ray spectrometer that's been adapted for the harsh lunar environment as well as to ride around on a miniaturized lunar rover.
What would you use a spectrometer, X-ray spectrometer for on the lunar surface?
We've tried to keep the instrument as versatile as possible. So there's many different science experiments you can do. The big one is prospecting for the purpose of in situ resource utilization. And we can leverage the sun somewhat as a X-ray or alpha or radioactive source to illuminate the regolith, and then leveraging X-ray spectroscopy, we can see what the rock-forming elements and hopefully their relative abundances in the regolith.
I like that, a lunar prospector of sorts.
Correct. There are also a couple of other applications. For the initial phase of the competition, we came up with a cool science idea that allowed measuring active regions of the sun to very high angular accuracy compared to what you could do with orbital assets. And that experiment was all about lunar rover mounted SunSlicer pointed at craters on the moon that could shutter or block the sun's X-rays as it rose or fall behind that crater, and then, get enough imaging information to map the size of those active regions. And then lastly, for free, you get radiation monitoring ability up into the high X-ray range, which is interesting to keep our astronauts safe when they return to the moon on the Artemis program.
Awesome. Thanks so much, Phil. Appreciate it. Let's go now to Tibor Pasher, who is actually in Budapest. and he's going to tell us about Water Snooper. Tibor, what is Water Snooper?
Hi, Blair. Greetings from Budapest. The Water Snooper is a very small, actually a neutron detector, which is able to look for volatiles, hydrogen and water ice on the moon surface.
How did you accomplish this task in such a small form factor for Honey, I Shrunk the Payload?
The idea is actually from our colleague David. He was thinking of how can we use industrial CMOS sensors to detect neutrons. This looks crazy, but we managed to put just 3 really good quality industrial CMOS sensors in this very small 10 times 10 times 3.4 centimeter box actually, and it looks fine. It works everything. The challenge was actually to put also the electronics into the box, but we managed that as well.
Now, the idea would be that you would put this payload on a rover, correct?
Yeah, that's correct. Actually, so if we manage to put the Snooper on a rover, then we can just go around and look specifically water if we know that the area is a potential area for water ice or hydrogen. On the other side, we can make a kind of prospecting map, looking at what is there actually, where it would be useful to dig for water ice. So the Snooper is able to look about 1 meter into the regolith, and this is the upper region of the regolith where we expect to have water ice. And if we know how much is there, how much water equivalent hydrogen is there, then it might be a good chance for somebody to follow up, dig it up and make water and then hydrogen and oxygen from the water ice.
That's awesome. Tibor, thanks so much to you and your team. And I want to thank everybody who joined us today, all the participants for Honey, I Shrunk the Payload. We wish you all the best of luck and hope to see you all fly these payloads to the moon. Thanks, guys.
Thank you so much.
What really impressed me about these teams, guys, is the fact that they've taken technology and miniaturized it, basically shrunk it down for the challenge. But all the things they're looking at are all things that NASA needs to accomplish for us to develop a sustainable presence on the moon in Artemis.
That's a great point. NASA's not going to be able to do it alone. We're going to need, commercial industry, academia, other government institutions, the international community, and the general public. And this is a great way